For being up this early. So this talk was originally to be given by David. This is work that we did with David for his thesis, and he has, for personal reasons, he decided that he couldn't make it. Okay, so range decomposition. I'll tell you what that is. So here's the outline. We always got to put an outline there. Well, let's just move on and get to it. So here's some obligatory application slides, courtesy of Rob. That we want to solve these rather complicated problems, and we're all trying to do it in parallel and break them into pieces and do a little piece on each processor. So this is a different way to do that. Here's a computational, how do we get computational problems? You all know how this flows, right? And where we're going to try to do some parallelization is right in here between those two. Okay, so RD, range decomposition, parallelizes at the PDE level. Okay, how are we going to solve these PDEs? Well, over the last 20 so years at our group, we've been working on a methodology to solve PDEs that starts with a first order system least squares discretization. Here's some nice things about that. There's a minimization that's measurable, local error estimator, and this is going to become important that this is what we use for a local error estimator. It's the functional, or the residual after you've gotten the guess. And what that leads to is adaptive refinement, and we wind up doing the adaptive refinement that has equal distribution of the functional error. Okay, multigrid. I don't have to tell you I'm multigrid, right? It's a good algorithm in serial. Get you order n. Parallel implementations. There's some really terrific parallel implementations. This is a different way to parallelize things. All right. So what is this nested iteration? This is the key to what we're going to be talking about this morning. And that is you start on a coarsest possible grid, and you solve something on the coarsest possible grid. Maybe it takes you a V-cycle to do that. Then you do adaptive refinement at this point and inject the solution into a refined grid, and you solve it on that fine grid, and then come up through grids, building the grids as you come up. Even starting from as small as some of the MHD calculations we did. We had a 4x16 grid and went 22 levels of refinement, sometimes double. Okay, so you wind up getting a nice grid out of that. Doesn't multigrid scale? Well, just the V-cycle scales in some sense. The cost to perform a V-cycle scales well. But if you're going to a finer and finer grid, then if you start on the finest grid, you're going to have to take more V-cycles because you want, you have lower discretization error, so you have to take more. So really, that has to get in. It's an extra log, right? Solving on increasingly finer discretizations requires an increasing number of V-cycles, so you get an order n log n. However, if you do nested iteration, that isn't a problem. You wind up getting order, you wind up getting order n back because you started on the coarse grid, solve things there. So this is an FMG cycle or nested iteration. The difference there is for nested iteration, we don't know what the grid's going to be when we start. But, okay. So here's parallel multigrid, and this is, we all know, the dilemma on parallelization. If you chop up the domain in this way, and here's processor boundaries, you have to communicate across the processor boundary. And what do you have to communicate? If I have little n squared guys in here, then I have to do n across the boundary. That's the bandwidth, and of course that goes down as you go down the levels. Now I have a smaller bandwidth, but the same number of communications. And in fact, when we get down here, smaller bandwidth, but the same number of communications. And even if we get to the really place where we're not even talking to each other across the boundary, they got to do some longer distance, you still have, everybody has a latency, even though it's one guy they're sending around. And that's the issue for just straightforward parallelization of multigrid, a V-cycle. So here's the idea we have. I'm going to try the idea of goal of less communication, and we're going to do more local computation, and we're going to sacrifice some accuracy for the overall solution. So we're getting a little bit less accuracy, much more local computation, but we're trying to get accuracy per cost, the wall clock is what we're looking at. The work we're going to talk about is similar to something that Aki, of course Aki probably mumbled something about everything we do today a long time ago. And Bill Mitchell wrote some things about this, and recently Randy Bank and Mike Holtz. But they did it in a domain decomposition way. We're going to talk about range decomposition. And here's what I mean by range decomposition. Okay, we're going to solve a PDE, and this is how we're going to state it. That's could be a big first order linear system, could be nonlinear, but okay, so here's some boundary conditions. What we want to do is decompose the range, not the domain. Everybody decomposes the domain. Let's do the range, because what we want to do is distribute the work or distribute the error. Okay, we could decompose the right-hand side if, you know, we think that could be a residual from a previous iteration or something. That tells us where the error is, how big it is. So we want to chop it into pieces where these are all approximately equal, if that's our error measure. One way to do that, and that's what we're going to talk about today, you can think of other ways. Partition of unity. We take a partition of unity, chi I, and we multiply it by f, and chi I has some compact support. So each processor is going to have a little different chunk of that. Okay. So we're going to solve in parallel for each of these over all the processors. So we have a different problem on each processor, where the right-hand side is what it used to be, or the residual, what it used to be in some portion of the domain, and 0 everywhere else. Okay. So now, this guy is defined globally. That's the important key. I'm not doing a domain decomposition. I'm doing a global solve, and then when I'm done, I have to add them up. But until I add them up, I don't have to talk to each other. Okay, I have to talk maybe when I break it into pieces, and I go away and do all this processing, nested iteration, starting at the bottom, going all up, adaptive refinement, and going on through the grid. So here's another look at this algorithm. There's a pre-processing step, and you think of all the processors sitting there. They know something about the problem, and they all, in parallel, start solving it. Each processor solves the entire thing on a really coarse grid, just some fraction of the strength of the processor or the cluster of processes. Solve it on a coarse grid. No communication yet. Choose a partition of unity. If you solve it on a coarse grid with nested iteration coming up through it, and you use a space-filling curve to order your elements as you're coming up adaptive refinement, each processor knows on processor 13, I have to take I've divided the error, the residual, into 13 or 50 or whatever it is, and I take the 13th chunk. So without any communication, it knows what its partition of unity is. Each processor knows its problem. So there's no communication yet to get this really coarse grid, distribute the error roughly equally, and then we go through this process of forming a residual. That can be done locally. I decide what my problem is, and now I'm going to solve a global problem with a different chunk of the right-hand side. No communication yet. The only communication comes in where I need to sum the guys after I do all of this solving with the whole nested iteration full multigrid algorithm. And then I add it all up. I add it to my current solution. I get a new solution. I can do it again. You can repeat this process. So there's one place you have to do basically an all-to-all communication. So the solve that we're doing here is nested iteration using adaptive mesh refinement and AMG as the solver. Okay, so the sum requires a union of the grids. So let's look at a problem. I'm going to try to make the simplest possible thing. Of course, 4x4, we don't 2x2, a 4 processor computer we don't care too much about, but this illustrates it. So I have 4 processors, and suppose I've done an initial thing so that the error on each of these pieces is about equal. So then we divide this thing, and each processor now has a global thing, but for example, this guy has non-zero right-hand side here and 0 out there. Let me see, this guy appears non-zero and 0 in those 3 and so forth. And you see, as we refine, it starts paying attention to its own home turf. because outside it's 0, and that's the measure we're using for the error. So it's going to start out not doing anything out there. So as we go through refinement, almost all its attention will be paid to up there in that corner. And we'll talk a little bit about this in a minute. Yeah, I'll get back to that. So here's an example problem, just a Laplace equation with some lumpy looking solution. And each processor has done its own solution. And then you add them together, you get the right thing. Okay, so what have we done that makes it less accurate? Well, if each processor was doing a domain decomposition, it would have all of its energy up in here. In a typical domain decomposition thing. Well, we've got these extra degrees of freedom that we've used. At this point, this processor needs to know this portion of this processor's solution. Needs to hand it over here and add it in. He needs to know this portion of this processor. He needs to know this portion of this processor. So you do that, you pass it on, but you see you could pass this to this, you can add it together, and after that add it together, and then go to there and add it on. So as you're communicating, you can pass it on. Maybe you can add it on. Also, I want to point out, if you look at the number of points outside, it's a small fraction of the total number. This is the magic of multigrid, right? On a graded grid like that, the percentage outside is small compared to that. In this one case, it's probably 95% is inside the region. However, you don't get quite as fine a grid here because you've had to use this as if you'd done, domain decomposition. So you lose a little bit of accuracy, but you gain some other things. So what am I doing here? I think I said all this stuff. Along the way, you have to union some grids because if I'm going to take this guy, well, but this guy, pass it to him, and then he's going to pass it up here, you have to take the union of these two and add them. So it's a union of those grids. So that's a little bit of stuff there, but that's all in a local processor problem. So here's the model for communication. You know what the latency and the bandwidths are. And in this model, we're not even going to bother looking at the computational part because, according to someone here in the audience, flops are free. Right? Okay. So we'll forget about that part and only look at the communication. And of course, here's the number of messages, the total data pass. Here's just the parameters. I'm going to go through this quickly. So here's an important one we want to talk about. Each process or processor or cluster has resources for E elements. That's just, if each processor has enough for your problem to do 10,000 elements on his processor. That's E. The total number of elements that I could define on the whole thing is then P times E. Each processor has this much strength. That's his strength. And so the number of nested iteration levels is something to do with the log of E. If I started on a coarse grid that's about the size, the number of elements is equal to the number of processes, then the number of nested iteration levels will be about this. Okay, so the traditional model of just doing the whole thing all at once would require this kind of bandwidth and latency. And we're going to assume that E is fixed, but it's larger than the number of processes or clusters. Okay, better go a little bit quicker. For the RD, the range decomposition model, we have to worry about the number of elements that are inside my home turf over the total number of elements I have on that processor. I have to worry about that ratio, and that's something like 90% in a lot of cases, or it can drop, but we'll see. So here's the number of exterior elements. Q times E is the number of interior elements. So this is the stuff we sort of, quote, waste. I'm going to go through this really, really quickly, but you do this thing where each processor throws half of its guys to another guy. It's a butterfly thing. And it would, trust me, it's just, you do it, you send stuff, a whole pile to the next guy, and he adds what he has and passes it on. Okay, so I think I better go a little bit more quickly here. So we did the analysis. This was what the guts of David's thesis was. And then just go to the bottom line. Here's the traditional way of doing parallel multigrid and the latency and the bandwidth. And here's what the RD model goes. So it's a lot smaller in the latency And that's one of the things that really kills you. And if the processors and the number of E is balanced, you have this thing going on. Well, there's another thing. We can reduce this so that this is square root E and that's a square root of E. Because as you're passing information along, and the one process is gathering all the other guys' outside stuff. When it gets to him, all he needs to know is the boundary. Because then he can redo it. I mean, flops are free. Right? So he can redo it because then he has the boundary with the 0 right-hand side. It's what we call an L-harmonic contribution. So we can get down to this kind of numbers here. So you see it's a little bit less communication. Did this sort of performance modeling, and he went to Stampede, yeehaw, which is a computer in Texas. And he actually measured all this stuff. So the latency was like 500 times the bandwidth costs for alpha and beta. And when you do that, then the role of the bandwidth and the latency are switched between traditional and RD. And in the tests, a lot of numerical results is Q. The outside thing is about 30% on some of this stuff. It's less. Well, I'll show you that in a minute. It can be less or it can be about that. It's what we want to keep it. So we did some tests from 16 to 1024 processors, began in a coarse mesh with P elements, where P is the number of processors. So we solved it there, distributed the error, and for the pictures I'm going to show you, we're going to assume it was equal to begin with, because it's just easier to see. We allowed about this. E was 4,000 elements per processor, so this is bigger than that by a factor of 4. That's about all you need, about 4. So we did timings. Here's the problem we solved. Is basically a Laplace equation. So you define capital U, the gradient little of P, and then you have this div curl part. Okay, so that's for the first order system. We started with a problem that was highly oscillatory. So there was a bunch of wavelengths within each processor. So it looked like that's random error. So here's what it looks like after you do. There's one. So this is on 64 by 64. So here's a guy here in the middle. I think that's 64. Anyway, this is what it looks like. This is the mesh that's generated by nested iteration to solve that part. And you can see it's mostly where you want it to be, and then it's got this graded stuff. And FOSS-PAC demands a 2-to-1 grading, so it's probably graded more outside than it really needs to be. Here's on the second iteration. It's even more tight. Go to a corner. That's what it looks like in the corner in the first iteration. Second iteration. Here's some weak scaling. So here's the first RD iteration. And the second RD iteration, as you get closer, it gives you different sort of weak scaling. This was traditional, starting to grow at 1024. The effective mesh spacing has got this Q in it, whereas the traditional would be 1 over the square root of EP. It's 1 over the square root of the number of elements, right? Because their elements are 2-dimensional. So this is what you lose. You lose a little bit of H. So when you put that into your error bound, this is how much you lost. Okay, and we have some theory. Actually, this worked way better than I thought it would. So I had to go prove what the heck it's doing, right? So here's what traditional would get. Here's what RD gets for its error. And if we look at the ratio of elements to processor, as long as you're, 10 or more up here, it's in an acceptable range. If I get 1 element per processor, it's going to suck. So you need enough guts on each processor. So here's what we want. E much greater than P. So here's that 64 processors. The Q is 0.86. This is the error coming down here, the relative error reduction. If I do a traditional method, it's going to get this green line. Here's 1 RD step, 2 RD steps, so forth. Traditional took 11 seconds. 1 RD step took 2.5. It's got less accuracy, but a lot less time. Okay, so you're sacrificing accuracy per time. Then you go to more processors. These lines move, but I still get with indiscretization error on the first step. And that was what puzzled us until we proved why that is true for elliptic problems. Okay, I'll go through real quick. Go through there. When Q is poor, we don't get enough. When E is not sufficiently large than P, we have some problems. This is one of my favorites. I like to look at this. This is the reduction in the error to the 1 over time. The accuracy per computational cost, right? And we see that RD with 1 iteration actually beats with 2 iterations, even though we're getting a lot closer on the 2nd iteration. If all you cared about was, if you were paying somebody for the computer and you wanted the most accuracy per cost, that's where you stop, 1 iteration. Here's the number of processors. Then this changes it. What if I had to pay for not the machine, but I had to pay per processor? That changes what happens here. So, but that's another story. It's a different payment. So here's some interesting thing. This was, let me quick, that's advection. So here's an advection problem. You might say, well, if I've got a processor over here and it's got a sharp gradient over here, what's going on? So let's look at that. Here's a corner element. Yeah, it has some stuff outside. On the next iteration, it doesn't. Let's go to a middle element. Yeah, it has some stuff outside. Not a whole lot. On the next iteration, it doesn't, and so forth. This actually worked pretty well. So here's the conclusions. If E is significantly greater than P, then performance model predicts that RD communications will scale much better than traditional. Extra computational cost was small. Effective error reduction on the iteration depends on keeping Q close to 1. The range RD discretization error and the traditional discretization differ by a factor of 1 over Q. You get within discretization error in 1 step of this. Amazing. I was blown away by that. Accuracy per cost, RD wins. Okay, what if P is bigger than E? What if I have really dumb processors like the old connection machine? Remember that one? We cluster the nodes. So you have nodes cluster and these hierarchical machines that are being developed would work. There we go. But that's a story for another day. Thanks for your attention.